come to that. So what is one view of a singular value decomposition, right? So here is one interesting view. So here I am calling the matrix to be M actually. Oh, the V transpose is the same as V star. Okay. So one interesting view of the singular value decomposition is when we consider the matrix M as an what we call is an operator. So what is an operator? So when I say a matrix, so there are two views of a matrix, frankly. So I mean, very broadly, keep this in mind. A matrix, you can think of a two-dimensional array of numbers. That's one view, right? Another view of a matrix is that it sort of takes a vector, right? That it takes a vector in Rd and gives a new vector in Rn, right? Which means that it's taking Rd and giving another vector in Rn, right? For every vector in Rd, it's giving a vector in Rn, right? As in, think of it as a function. You can think of a matrix as a function, right? In fact, it is what is known as a linear function. Any idea what a linear function is? So a linear function is very simple. It says that linear function, a function f is linear if f of x plus y is fx plus fy. Basically, it's linear. That's what it means, right? So one view of a matrix is that is as a function, sort of going from one dimension to another dimension, from Rd to Rn, one dimensional space to another dimensional space, right? And the way you look at it as a function is just that you multiply any vector that you are given by the matrix, you get another vector. Okay. So why is this important? Right. So this is important because this is one very nice way of explaining what is the singular value decomposition is doing. Right. So now if you write down the matrix M in terms of the singular value decomposition, it's easy to see what a matrix does to a vector. Right. And it's very kind of cute. So imagine that in Rd, right? In Rd you have you consider the unit ball in Rd. So what is the unit ball in Rd? It's nothing but it's not. I mean, so consider L2. So the unit ball is L2 is nothing but the unit circle. Okay? Similarly, the unit ball in Rd is really the set of all vectors in Rd such that the 2 norm is 1. Right? X belongs to Rd. Okay? So consider any vector. I mean any two vectors in the unit ball. Okay? Let's see what's happening to them when I multiply by M. So multiplying by M can be considered as three operations. That first I take this vector and multiply by V transpose. Fair enough? Now V transpose has a property that it's really what is V transpose? V transpose is a R by D matrix, but it has orthonormal rows, right? So what does it mean? What does it mean to the length of a vector? So consider this is vector I. So what is the norm of V transpose x if the norm of x is 1? The norm of V transpose x is? The norm of V transpose x is 1. Right? Yeah? Okay. So what does that mean? That means that if you were looking at the unit ball in this d dimension, right? You have gone from the unit ball in d dimension to the unit ball in r dimensions, because V transpose takes a vector from d dimension and puts it in r dimensions, right? This is V transpose x belongs to capital R to R. Okay. So basically, it's like saying that you have taken a unit ball from that I've drawn on the surface that, let's say, that I've drawn in this 3D, and you have put it in a smaller dimension, in a smaller dimensional space, right? But the shape of the unit ball has not changed. Unit ball still looks like a unit ball. But now what is interesting? Now what happens? Now in R dimension, we multiply it with a diagonal matrix sigma. The next step of multiplying with M, right, is that you multiply x with V transpose, then the result you multiply with sigma. So what does multiplying with sigma really mean? Multiplying with sigma. So what is sigma really doing? Sigma C. Sigma is nothing but sigma of x. See, x now belongs to R of R, right? Because so sigma of x is really sigma 1 x1 sigma r xr. Fair enough, right? It does nothing. It just does a scaling of the individual coordinates. So sigma is of size r by r, and this is of size r. So it basically just scales individual coordinates. So now I have taken the unit ball in d dimensions, and I have put it in r dimensions, and now in r dimensions I am stretching the unit ball in different ways along different directions. Okay, so the unit ball in r dimensions becomes a ellipsoid in r dimensions, right? But now I am going from the ellipsoid. Now the last step. So I have done V transpose x, I have done sigma x, and the last step is multiplying this quantity by u. So I have to consider what happens to, let's say, u of y. What is the norm of u of y with respect to the norm of y? What is the norm of u of y with respect? So remember, u is an orthonormal matrix. What does that mean? So what is the vector u of y? U of y, you could write it as a vector as so basically you take y, you sort of so yi is the ith coordinate of y, and u I star is the ith column of u, right? So the norm of ui is really the norm of this vector, right? But now these are orthogonal to each other. So therefore, using Pythagoras, this is nothing but the norm of, which is equal to the norm of y, right? So then again, what is u doing? So u is taking an ellipsoid in RR, and where is it putting? What is the dimension of uy? What is the dimension of ui? So A is of size n by d. So u is of size n by r. So this goes to Rn, right? So then what is it really doing? That it's taking again the ellipsoid in a lower dimensional space and just placing it in a much higher dimensional space, but the shape of the ellipsoid doesn't change because the norm of every vector remains the same, right? So see, this picture will be kind of useful when you think of what the visualization sort of how PCA or how SVD is helping visualization, right? Is sort of helping you sort of visualize data, right? Because what is really happening is that the singular value decomposition then tells us how a matrix sort of acts as an operator in sort of changing data, and it sort of breaks down the operation of a matrix on any particular vector in terms of three operations really, right? One is a projection into a lower dimensional space, that's the V transpose. One is the scaling, right? And one is a lifting, that after you have scaled, a lifting of the matrix into a higher dimensional space. That's really what it is. Okay? So just keep this in mind, and we'll come to this at some point again. Okay? So now suppose let's kind of take another view through PCA, right? That suppose now we say that suppose now we are not considering the data, we are not considering the matrix as an operator, but as a much simpler object. Suppose we are saying that each row of M is really a data point in d dimensions, and there are n rows, right? So then these are all, this is the space RD. This is the space RD, and then there are n points here. Okay, So now I'm asking a much more simpler question, maybe, right? Maybe it's a much simpler question. That what is the best line through these data points? Single line. What is the best single line through these data points? I mean, in terms of minimizing this error, right? That what we are going to do is that we are going to project every I mean, we're going to try to fit the best possible line that goes through this in by trying to minimize this orthogonal projection error, right? And the way to do this is try to fit a line so that this quantity is minimized. Okay. Okay. So now, what is one way of writing this quantity? One way of writing this quantity is really that you take the matrix A, right, and then you multiply it with a V, right, and then you take the 2 norm of this vector. So do we know what is the 2 norm of a vector? Okay. So I mean, the 2 norm is really just the Euclidean norm, or this is what it is. We take the 2 norm of a vector, right, and because the norm of V doesn't really matter, because I mean, I'm really interested in the direction of the line, I might as well divide by the norm of V, right? I want to maximize this. And I want to find, okay, what is this V? Okay. Suppose this is a question that we're asking, right? So what is an interpretation of this? This is this means that if I'm able to maximize this particular thing, what do I get in very English terms, concrete English terms? I get the best line that's going through my set of points, where the best is in terms of capturing minimizing the orthogonal distance, or rather maximizing the orthogonal projection. They are equivalent by sort of Pythagoras theorem, because one of them is really the one minus the other. I mean, the norm of the vector minus the other, right? So either I could try to minimize these distances, or try to maximize these values, right? And here we're trying to try to find the V that maximizes these set of values, right? Okay. So suppose I mean, let me draw in 2 dimensions. That suppose the data lies in something like this. Yeah. Suppose the data has this kind of an ellipsoid form. So what would be a rough direction of the line? What would be a rough direction of the line? It would kind of go through this, right? Kind of like the major axis of this ellipsoid. This is the line that we're interested in. Okay. So this is my first step, and my question is that, what do I really get? And my claim is that look, what you really get is nothing but so remember my decomposition of A as U sigma B transpose? Oh, maybe I forgot to tell you this, and this is fairly important. This U is called the left singular values, singular vectors. These are called the right singular vectors, and these are called the singular values. Sorry, I completely forgot to give you the name, right? And my claim is that even if you approach the singular, even if you sort of approach this question from a different point of view, in terms of fitting the best possible line, right? What you really end up getting, right, when you're trying to fit the best possible line, what you really end up getting is one of the columns of V. In fact, it's a column of V that corresponds to sigma 1, where sigma 1 is a maximum. So basically, suppose sigma, I mean, as we arrange the sigmas, that in a decreasing manner, sigma 1 is a maximum, and then you look at the first column of V, right? And the claim is that what you get by doing an argmax of this is really just the first singular vector, right? But now suppose we're trying to do more, right? So now that we have found, if the data is like this, now that we have found the best 1D representation of the data, now we are greedy. Then we are trying to say that, okay, maybe 1D, the error itself is too much. 1D is not a good enough representation. What would be the best 2D representation of the data, right? I mean, we could try to just do this, as in we could try to just do that, saying that, okay, V2 is argmax of AV divided by norm of V, where V not equal to V1. Is this enough? Is this a good enough definition of the for trying to find out the second, for trying to find out a two-dimensional representation of the data? No, why should it be perpendicular? V should not be equal to alpha times V1, okay. But is that enough? So let's say we are regarding V and V1 as unit vectors. So then the alpha is naturally 1. But is it enough to say that, why don't we say that V not equal to V1? Why isn't that enough? Because then what would happen is that see, the shape of the data is something like an ellipsoid, right? Then although, and this is what I've taken as V1, right? Then what would happen is something, even if I say that V not equal to V1, something that's very close to V1 will come as V2, right? Maybe a slight perturbation of V. So basically it will not really capture much new information beyond what is captured by V1, right? That's why in order to force the fact that V2 should really capture information or distance structure that is not sort of maintained by V1, see, what does V1 not capture? Supposing there are 2 points here and here, right, that both of them are orthogonal to V1. So both of their projections fall at the same point in V1. So V1 has no information about the distance between these points because it doesn't preserve the distance between these points, right? So now what I'm trying to say is that let us look at the information in a slightly vague sense that V1 doesn't preserve at all, right? And let us try to capture that information. And for that we put in a constraint that let us look at all the vectors that is orthogonal to V1, right? And then we try to maximize this, try to do an argmax of this. And the claim is that this is again nothing but the second singular vector of A, the second right-hand singular vector of A, right? And we keep on going. We keep on going until we get VR, which is argmax of VR orthogonal to V1 to VR minus 1, AV by norm of V, right? Yeah, and you can get out only R of them, right? Because these are all, this V1, V2, VR are again an orthogonal basis of the column space, of the row space of A. And because the rank of A is R, there can only be R of them. Okay. So now let's turn the question around, right? That supposing I say that A is n by D, right? Supposing the data was in the columns, not in the rows. How would I phrase this question? How would I sort of cast this in a way that I'm trying to find the best one-dimensional line, then the best two-dimensional hyperplane, and so on. What would I write in terms of, instead of writing AV, what would I write? If the data is in the columns, if I think of the columns as the data rather than the rows. Norm of AU by, see the norm, there's no difference between writing norm of AV and norm of AU. You're just changing the, going from here to here, we're just changing the name of the variable. Right? So you're close, I think you have the right idea, but A transpose. So A transpose U or V by norm of U. Right? That's what we need to do. And what would you get? You would get the left singular vectors. You would get the left singular vectors of A, right? You would get U1, U2, U3, etc. Okay. So in fact, there's a very interesting theorem. We don't have time to go through this, but this characterization of the singular vectors also suggests sort of a very nice algorithm for actually finding out the singular value decomposition, because I only define the singular value decomposition for it, and I claim that it exists. I never gave you any, how to find it, right? But what this algorithm suggests is that really the way to find it is as follows, that first find this V1, right? That first find this V1, right? By trying to do argmax of V by norm of V. Okay, and how do you do this? You do this through what is known as power iteration. Right? That basically you multiply, you start with a vector V, you multiply that by A, then you normalize it, you multiply that again by A, you normalize it, multiply that again by A, not by A, but rather by A transpose A. Right? You do power iteration, right? And then you keep on going. Okay? So we won't go into the details of that. So and once you have gotten that, then you want to remove V1 from A. So what do? You do basically A, you do I minus V1 transpose of A, right? What is that doing? That's saying that let us take let us project A into the subspace that is orthogonal to V1. That's because now we are interested in directions that are orthogonal to V1. So we are completely removing V1 from A, and then we again do power iteration, right? So this suggests a very natural algorithm for doing SVD, and you can show that it's not very hard to show that whatever the V1, V2, VR you are getting, that's exactly the same as the singular vectors of A. Right, and there's a very sort of there's a very nice induction based proof of that. I was thinking about proving that, but I don't think we have time for that. Let us skip that proof. Okay, so now let's come to something that comes from the concept that comes from the singular value decomposition, right? So we said that we want a low we are given a K. We are given A equal to U sigma V transpose, and we are given a target K, and we want to say that for each row of A, let's say, find low dimensional representation. So how would we actually find the low dimensional representation of A? Right? Because our whole target, our whole motivation of going into this SVD and all was to find out low dimensional representation. So what is the low dimensional representation of A? Okay. So here is one interesting way of looking at this, right? So look at what is happening. Let me write U as follows: U1, U2, UR, sigma 1 to sigma R, see the way I have written, so this is exactly the same as what is here. I have only denoted each column of U of capital U as U1, U2, UR. I have denoted each row of V transpose as V1, V2, VR. That's it. Nothing else has happened, right? But now that I have written this, there is a very interesting way of doing the product. Now we can write this as sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose sigma R UR VR transpose, right? Basically, first you multiply sigma 1 sigma R with V1 transpose to V2 transpose. So each sigma multiplies the corresponding VI transpose, and then you have the matrix U1 U2 UR, and then V1 transpose to say V1 transpose sigma 1 to VR transpose sigma R, and then you just do a dot product like thing. Okay. What is the dimension of this? What is the dimension of each of these terms? N cross D. See, these are all matrices. These are all matrices, N cross D. What is the rank of each one of them? No, rank of each term. Rank of sigma 1 U1 V1 transpose. What do you think the rank of that is? So the rank of that is the same as the rank of U1 V1 transpose, because sigma 1 doesn't matter. And what is the rank of that? What is T? Huh? D. This is a n by D matrix. I haven't said whether n is small or D is small, but that doesn't matter. Okay, let me ask a simpler question. What is the rank of A transpose? If A is a vector, n by okay, we'll do that in the tutorial today. The rank of A transpose is 1. In fact, the rank of A B transpose is 1 for any two vectors A and B, right? And it's not very hard to show. You take any two columns of A, you take any two columns of this matrix, and then you can say that one of them is really a sort of scaling of the other one, right? That's all that you have to show. So each of them is a n by D matrices, right? And each of them has rank equal to 1, right? And think of this sigma 1 to sigma r as sort of the scales, right? So it's like saying that I have written A, that I've taken A, which was a rank R matrix, and I've broken it down into a sum of rank 1 matrices, right? And I have given the first rank 1 matrix a weight of sigma 1, second rank 1 matrix a weight of sigma 2, and the rth rank 1 matrix a weight of sigma r, right? And it is known that sigma 1 is bigger than or equal to sigma 2 is bigger than or equal to sigma r. So the weights are decreasing. Okay. So now what will happen, interestingly, is that if I want to get a, let's say, a rank k representation of A, right? And in some sense, I mean, I'll define it more precisely. In some sense, I want to get the best rank k representation of A. What is a natural way of sort of that after you look at this decomposition, what is the natural way of trying to extract out the most out of this decomposition? Because remember, the weight sigma i's are decreasing, right? So then the natural way of taking the most out of this sum is by taking the top k prefix, because sigma 1 is kind of going to have the most weight, right? So take sigma. So if I'm interested in taking the rank 1 representation, take sigma 1 E1 V1 transpose. If I'm interested in taking the rank 2 representation, take the first 2. Taking the rank 3, take the first 3, and so on. So this actually is called AK. So let me call this AK. Is really the sum I equal to 1 to k sigma I Ui Vi transpose. So this is the intuitive definition of AK, right? And what we'll then see is that this intuition that we mentioned actually carries a lot of weight. That this AK is really the best rank representation of A in a number of ways, according to a number of definitions, right? So let's go over these. Okay. So in fact another way of looking at AK is as follows. That if you look at the vectors v1 to vk, right, which are the top k right singular vectors, right, and if you look at the subspace spanned by them, let's say V is the subspace spanned by them, or V is the matrix that has these columns, right, you can say that one row of AK, let's say that the AKI star is really nothing but you take the corresponding row of A and then you project it onto the subspace. So this is the operation and this is the picture. That supposing this is the space V, right, which is really spanned by V1 to Vk. What is happening is that here is a row of A, AI star. We are projecting that row, right, onto the subspace, and what you would get is really the corresponding row of AK. Okay, so basically by taking this sum, see we arrived at AK at according to a slightly different definition, right? By taking this prefix of this rank 1 matrices. However, it takes a little bit of algebra, not much. You'll be able to do it yourself. To say that if you take every row of row of A and project it onto the subspace spanned by V, which is obtained by the matrix VV transpose. VV transpose actually is nothing but a projection matrix. That is the, and multiplying any vector by the matrix VV transpose is really projecting that vector onto the subspace spanned by the rows of spanned by the columns of V or the rows of V transpose, and that really gives you the corresponding row of AK. Okay, so that's really one interpretation of AK. Another interpretation of AK, and why is this good? Okay, so this is good in this following way. So for that we need to define what is known as matrix norm, and have these been defined? This should have been defined in your linear algebra class, the Frobenius norm and the L2 norm of a matrix. Yeah. Root of close enough. A transpose A is a matrix. So what does root of A transpose A mean? Root of the trace of A transpose A. You could write it as root of the trace of A transpose A, but I like to just, there's a much simpler definition. Basically you take, it's nothing but the root mean square of all the entries. So think of the matrix as a long vector, take the L2 norm of that. It's a root mean square of all the entries. So there is the 2 norm of a matrix. What is the 2 norm of a matrix? The first norm is known as the Frobenius norm. What is the 2 norm of a matrix? The 2 norm of a matrix is exactly that. That you kind of multiply a matrix by a vector, and then you say that, okay, let me find out the vector that gets distorted the most in some sense after multiplication. Okay, that if the vector was originally of length 1, I look at its length after multiplication and I see which vector gets distorted the most, gets increased the most, gets increased in the norm. Such that the ratio of AV to V is the highest, and that ratio is the 2 norm of a matrix. Okay. So now let's look at the Frobenius norm. Okay. Now here is this very, very interesting theorem that says as follows. So see, one very natural sort of way to think about 2 norm is to think about Frobenius norm is that suppose we have a matrix A and we are trying to represent it by a matrix B. Right? Let's say B is a simpler representation of A. And one way of taking a simpler representation is by saying that B has rank K only, where K is small, right? And I want to say that how close A and B are. So the way to see that is by taking the difference A minus B and looking at the root mean square error, which is exactly the Frobenius norm. Okay. Now I want to say that, okay, give me the B, right? Find out B such that B is of rank K and B is closest to A. This was the problem I was looking to solve, right? This is really my sort of way of saying that I want to get a low dimensional representation of my data that is faithful to my data. So it's not enough to do any low dimensional representation. You have to capture as much information about the data as you can, right? And that we are measuring by saying that I'll take the difference of this low dimensional matrix B and my original matrix A, I'll subtract them, then I'll take the Frobenius norm of the difference. Right? And what is this matrix B that is closest to that of A? Right? And it turns out that the right answer is really the matrix AK that we have come up with. Right? That either you can think of AK as nothing but the projection of the rows of A onto the subspace spanned by the onto the subspace spanned by the top right singular vectors, the k right singular vectors, or you can think of it as a sort of that I'm approximating A by a sum of rank 1 matrices, and I take the first k rank 1 matrices according to the singular values. Okay, and the proof of this actually comes from the theorem that we saw from the that we kind of ignored the proof of. Okay, and this is why, and this is really the, and this statement really captures the importance of singular value decomposition. This is why, if you are, I mean, for most cases when you are dealing with the L2 norm or the Frobenius norm, and in fact I sort of ignored this, but even according to the L2 norm, this is true. Right. So this norm here, I've written it according to Frobenius. It can be the Frobenius norm or the 2 norm, or actually it can be a number of other norms also, but the Frobenius and 2 norms are the most natural. Okay. So any question about this? Okay. If nothing else, why are we looking? What is the importance of the singular value decomposition then? Anybody? Yeah. This side is more active, so let's get an answer from this side. Yes? Importance of singular value decomposition? Give me one use for it.
We are reducing the space and dividing the matrix into 3 matrices.
Okay. And? So we are using it to find one low dimensional representation of A, which we are calling AK, right, which is optimal in a number of ways. In specifically, when we are measuring the error with respect to the Frobenius norm, which is the same as root mean square norm, right, the singular value decomposition is the way to get the optimal solution to this particular problem, right. That we want to get a low rank representation of A that's close in Frobenius norm. Is this statement clear? If nothing else, this statement should be sort of drilled down in your consciousness.